Hi everyone, my name is Kuvina and welcome to Relativity Part 9. In this episode, we will be examining the most famous equation of all time, E equals mc squared. Despite being the series finale, it's relatively self-contained, so feel free to watch the rest of the series after this one. With that out of the way, let's begin. So E equals mc squared is the flagship equation for the concept of mass-energy equivalence, which says that every object has an intrinsic energy associated with it that arises from simply having a mass. Specifically, this energy is proportional to the object's mass, but multiplied by c squared, where c equals the speed of light. Since c squared is such a big number, it means even a small mass contributes substantial energy. Now for the most part, this energy is inaccessible, being stuck there as the object's mass. But there do exist notable exceptions, the most famous of which is nuclear fission. If you fire a neutron at a uranium-235 nucleus, it most commonly splits up into krypton-92, barium-141, and 2 extra neutrons. But the total mass of these output particles is a bit less than the originals, actually quite a bit less, about 1/5 the mass of a proton. So where did the missing mass go? Well, it got multiplied by c squared and converted to kinetic energy. So that's an example of how mass-energy equivalence is used and applied. But to get the full picture, there are a few unanswered questions we still need to answer. Specifically, where does the equation come from? What does it have to do with relativity? And why does the full version look so different? The rest of the video will be dedicated to examining these questions, and it will bring us closer to uncovering the mysteries of quantum mechanics and universal gravitation. With that out of the way, let's get into the derivation. Now there are two main ways to derive E equals mc squared, light waves and calculus. Unfortunately, both ways have shortcomings. Using light waves requires the wave interpretation of light as opposed to the particle interpretation, which is what most relativistic derivations use. And reconciling the two requires wave-particle duality from quantum mechanics. It also requires approximations that make it technically only a proof of concept, not a rigorous proof. The calculus approach, on the other hand, is more fundamental but requires calculus, and could be a lot less intuitive when it just looks like a bunch of numbers and variables doing weird things. I tried so many ways to derive it without light waves or calculus, but unfortunately I don't think a good derivation like that exists. So what I'm going to do is cover both ways, the light wave approach first, just as a proof of concept, and only after that I'll showcase the calculus approach, but in such a way that provides a physical intuition before each step. The light wave approach is extremely related to the relativistic Doppler effect. To explain the Doppler effect, we'll start with an analogy using particles. So imagine a photon machine that emits photons with a frequency of 1 cycle per second. You also have a receiver some distance away that takes these photons. What frequency does the receiver receive them at? Well, if both the source and receiver are stationary, the receiver will receive them at the exact same rate, 1 per second. That's because each photon follows the same path, just with a continually incrementing 1 second delay. But what if the source is moving? In that case, each subsequent photon now has a greater distance to travel before it's received, so they're received at a slower frequency than they're emitted. Additionally, due to time dilation, the source ages slowly in this reference frame, so the emission frequency itself is also lower. Deriving a formula for this is pretty simple. After emitting a photon, the source waits 1 second until the next. In our reference frame, it's moving at velocity v, so according to time dilation, it ages slowly, meaning 1 second to us is square root of 1 minus v squared over c squared seconds for it. This value is known as alpha. Going the other way, that 1 second for it to recharge takes 1 over alpha seconds for us. 1 over alpha also has a name. It's known as the Lorentz factor, or gamma, and is what we'll use from now on. In gamma seconds, the source travels a distance of gamma times v meters. The time it takes for a photon to travel this distance is just that over c. Each photon travels this plus the path of the previous one. So in addition to the gamma second delay between photon emissions, there is an extra v over c times gamma delay between when they're received, accounting for the extra distance. In total, we receive photons every gamma times 1 plus v over c seconds. After some algebra, this can also be written as square root of c plus v over c minus v. The frequency is the reciprocal of the interval, making it square root of c minus v over c plus v. And if the source's emission frequency is something other than 1, This just represents the ratio of observed frequency over source frequency. A cool feature of this formula is how it works in both directions. If the source is moving away from you at 0.6c, its frequency is cut in half, but 0.6c towards you becomes negative 0.6c and the frequency doubles. And we've actually seen this exact relationship in the twin paradox episode. Alright, enough about particles. In the wave interpretation, light comes not as a series of individual photons, but instead as one continuous electromagnetic wave. When a charged particle accelerates, it causes oscillations in the electric and magnetic fields that interact with each other in such a way that the oscillations propagate through space, according to Maxwell's equations. These waves have a propagation speed and an oscillation speed. The propagation speed is just the speed of light c and is constant in every inertial reference frame. The oscillation speed, on the other hand, relates to the frequency of the wave, which simply equals that of the accelerating charge. Since faster oscillations require more energy, the frequency of the wave is actually exactly proportional to the energy it carries, and this has massive implications. Going back to our example, instead of a machine that fires photons at a frequency of 1 cycle per second, we'll have a charged particle that oscillates once every second. Even though we're now talking about waves, the same ideas still apply: time dilation, extra distance, and invariance of c. So our formula for the frequency of particle emissions applies the exact same way to the frequency of wave oscillations, where they should also get slower with a moving source, meaning we've essentially bridged the gap between them. Furthermore, since frequency is proportional to energy, this also tells us how the energy of a photon changes across reference frames. Now, imagine the source emits a 360 zeptojoule photon. If it's moving away from you at 0.2c, the photon loses energy, becoming 294 zeptojoules in what's known as a redshift. If it's 0.2c towards you, it actually gains energy, becoming 441 zeptojoules in what's known as a blue shift. The reason for these names is that red light has a longer wavelength and therefore lower frequency and energy, while blue light has a shorter wavelength and therefore higher frequency and energy. The energies I picked for this example correspond to green, red, and blue light, but the same terms are used regardless of color, depending only on direction. With that, we've successfully derived the relativistic Doppler effect. Technically, this is only the longitudinal relativistic Doppler effect, where the photons travel parallel to the direction of motion. For other directions, you have to use the transverse Doppler effect, but it gets very confusing due to aberration, so I'm going to skip it. Anyway, now it's time to begin the E equals mc squared derivation. It starts with a stationary box with mass m1 and internal energy E1. Internal energy just means all types other than direct kinetic energy, so it could be chemical, thermal, elastic, etc. The box then emits L joules of light, dropping its internal energy down to E2. The light takes the form of two identical photons, each with energy L over 2, but in opposite directions to ensure the box doesn't move. According to conservation laws, total energy is the same before and after, meaning E1 equals E2 plus L. Rearranging a bit shows that the energy lost by the box is L. It makes sense so far, but now consider the reference frame in which the box is moving at velocity v. Since it's moving, the box now has kinetic energy, which is given by the formula 1/2 mv squared. We'll split it into before and after, giving us 1/2 m1v1 squared and 1/2 m2v2 squared. As for the photons, we just have to use the relativistic Doppler effect. The left photon gets redshifted to L over 2 times square root of c minus v over c plus v, and the right one gets blue shifted by the reciprocal amount. Total light energy is their sum, which after some simplification becomes simply L times gamma. We can now equate total energy before and after, and rearrange it to E1 plus 1/2 m1v1 squared minus E2 minus 1/2 m2v2 squared equals L times gamma. Now compare this to the version from the box's reference frame. Both equations are of the form box energy before minus box energy after equals light energy. Apparently, when moving at velocity v, that energy became gamma times more powerful. But here's the thing, if internal energy is reference frame independent, then the change in the box's internal energy, E1 minus E2, still only accounts for L joules of energy. After subtracting it off, there's a remaining L times gamma minus 1 joules of bonus energy. which must come from a change in the box's kinetic energy. But remember, we made sure the light wouldn't change the box's velocity. The only way for its kinetic energy to change is if its mass changes. After some rearranging, the mass it loses, m1 minus m2, must be equal to 2L times gamma minus 1 over v squared. It looks complicated, but this formula can actually be greatly simplified. Kind of. Take a look at the shape of the Lorentz factor graph, gamma in terms of v over c. It's not a parabola, but it is pretty close to one. Since parabolas are twice as wavy as circles, and gamma is approximately a circle due to being the inverse of one, the best parabola approximation is 1/2 v over c squared plus 1. The technical term is that it's a second-order accurate Taylor series approximation. Replacing gamma with this technically breaks the equation, but it should still be approximately accurate at most velocities. And by doing so, the right side simplifies all the way down to L over c squared. All of this together means that if an object emits L joules worth of light, its mass decreases by L over c squared. Since it's a loss, not a gain, delta m equals negative L over c squared. And remember, L actually equals the internal energy the box lost, making it negative delta E. Combining these gives us the relationship between change in internal energy and change in mass, resembling our desired form E equals mc squared. Now, as I mentioned earlier, the approximation of gamma makes this technically only a proof of concept. The reason it gave us the correct formula anyway is that the kinetic energy formula, 1/2 mv squared, is also only a low-speed approximation of a more complicated relativistic formula. As it turns out, these cancel each other out, providing the familiar equation. Due to this, as well as the assumption of wave-particle duality, the derivation might feel a bit unsatisfying. Additionally, it skips over concepts that, in my opinion, are way more fundamental to the idea of mass-energy equivalence than the relativistic Doppler effect. So, it's time for the second approach, using calculus and the foundations of physics to derive the equation. This process has 4 steps to it: forces, momentum, kinetic energy, and internal energy. This can be used to derive not just E equals mc squared, but actually 4 total forms of the equation, because in my opinion, you need all of them to get the full picture. Why start in this order? Well, it all comes down to kinematics versus dynamics. So far, we've only covered kinematics, which deals with things moving. But to understand energy, we need dynamics, which deals with the causes of that movement. And we're starting with forces because they're how the universe fundamentally interacts, such as electromagnetism, the strong nuclear interaction, and gravity. According to Newton's second law, force equals mass times acceleration, F equals ma. But this can't be true in relativity. Imagine there are 2 observers, stayer and mover. The mover gets in a ship with constant acceleration. In the mover's reference frame, they feel a constant force due to the acceleration. But in the stayer's reference frame, the rate at which the mover accelerates is actually slowing down as they approach C asymptotically. If you use this coordinate acceleration to calculate the force on the mover, it will underestimate compared to the force they actually experience by quite a bit. But how much? Well, we're going to derive an equation for it with the following scenario. The stayer is stationary while the mover is moving at velocity v and accelerating at a. After h seconds, their velocity goes from v to v plus ah. But in the mover's own reference frame, the velocities are different, so we have to combine with a minus v. Using the formula from part 6, we could see their velocity before is 0 and after is ah over 1 minus v squared plus vah over c squared. The time it takes is also shorter due to time dilation, specifically by the Lorentz factor inverse square root of 1 minus v squared over c squared. The average acceleration in this reference frame is just change in velocity over time, in which case the h's cancel. The instantaneous acceleration is the limit as h goes to 0, in which case this term disappears, and we get a lot of cancellation all the way down to a times gamma cubed. So if you want to calculate the force the mover actually experiences intrinsically, you can't use F equals ma, because you first have to convert acceleration from coordinate to proper. That involves scaling by gamma cubed, resulting in F equals ma gamma cubed, which levels off the graph. With that, we've derived an equation for how forces transform across reference frames, completing step 1. Now it's time for momentum. In classical physics, the momentum of an object is simply mass times velocity. It's represented by lowercase p, so p equals mv. The cool thing about momentum is that it's always conserved. For example, in the sliding block collision, total momentum is equal both before and after. But in relativity, things are complicated due to relativistic addition of velocities, and momentum as we know it is no longer conserved. To see why, we'll give the blocks relativistic velocities. Block A is 10 kilograms and moves right at 0.5 c. Block B is 10 kilograms and moves left at 0.5 c. Their collision will be inelastic, so instead of bouncing back, they merge into a stationary block C. Total momentum is 0 both before and after the collision, meaning it's conserved. But now, consider the reference frame in which the entire setup is moving right at 0.5 c. If you were to add 0.5 c to each velocity, momentum would still be conserved. But remember, in relativity, velocities don't add. Instead, using the formula, block A only goes 0.8 c, meaning momentum before is only 8 c, which does not match at least 10 c after. So why is momentum not conserved? Well, it's because p equals mv is actually not the full equation, rather an approximation that only works at low speed. To get the full relativistic equation, we have to take a step back and ask the following. What even is momentum on a fundamental level, beyond simply a useful concept? Newton's laws help again. As I mentioned earlier, the second law is F equals ma. But in its original formulation, he actually had something else in mind, which is that force is the rate of change of momentum, or in calculus terms, F equals dp dt. In this sense, momentum can be fundamentally thought of as the thing forces directly act on. So a force is just some way of transferring momentum from one thing to another, which also relates to the third law and why it's conserved. Combining this with F equals ma, all we have to do to derive momentum is integrate ma. Or at least that's how it goes in classical physics, but in relativity, we have to use the corrected form from last step with the gammas, resulting in dp dt equals ma times gamma cubed. To solve this equation, we first replace a with dv dt, since acceleration is just the rate of change of velocity. Treating derivatives like fractions, or using the chain rule, we get dp dv equals m times gamma cubed, at which point we'll substitute in gamma. Now we just have to integrate, which is not too complicated, only requiring a bit of trig sub, and we get p equals mv times gamma. Technically, there's also a plus c in there, the constant of integration, but to make momentum 0 at 0 velocity, c is simply 0. As you can see, this is just the classical formula scaled by gamma. This is why it approximates the classical formula at low speed, but increases infinitely as you approach c. This accounts for the extra momentum that objects must accumulate near c to keep things conserved despite the velocity nerf. That concludes step 2. Now it's just a matter of doing the same thing with kinetic energy. In classical physics, kinetic energy is equal to 1/2 mv squared. Just like momentum, this is only a low-speed approximation of the correct relativistic formula. Even though total energy is conserved, kinetic energy isn't necessarily, because it can be converted to other forms like sound and heat, which is what happens in inelastic collisions. But for energy, there's an even stronger intuition for why the classical formula won't hold up. The common explanation for why you can't go faster than c is that it requires infinite energy. But according to the parabolic 1/2 mv squared, every object has a finite amount of energy that will bring it past c as long as you make sure it stays kinetic instead of being wasted as other forms. The only way to prevent this is if kinetic energy increases infinitely as you approach c asymptotically. To find the exact formula, the process is shockingly similar to momentum. You see, in addition to being the rate of change of momentum over time, force is also the rate of change of energy, but over space instead of time. You're probably more familiar with the integral form, where work is force times displacement, but I prefer derivatives. To solve this equation, we'll multiply both sides by v. On the left, it becomes dx dt, position over time, chain rolling with dE dx to become dE dt. And now, just like momentum, we'll replace a with dv dt and chain roll to get an integral we can solve. The only difference is the extra v in there, but this actually makes the integral easier, only requiring a bit of u sub, and we get e equals mc squared times gamma plus c. Since the integral only concerned itself with change in velocity, this is actually specifically kinetic energy. This time, to guarantee zero kinetic energy at zero velocity, c is negative mc squared, which can be absorbed into the other term, forming a gamma minus 1. Don't get too excited, it's not mass energy equivalence yet, but it is the same mc squared we'll be seeing soon. It's a bit of an unsatisfying derivation though. It makes sense why m and gamma are here, but why the c squared beyond simply the chain rule? For that, we'll use a bit of geometric intuition. For the purposes of this intuition, we'll set m equal to 1 to simplify the equations. In that case, classical kinetic energy is the parabola 1/2 v squared. As I mentioned earlier, parabolas are twice as wavy as circles, which means a unit circle already approximates it. Gamma isn't a circle, but it is very close to one since it's the inverse of circular alpha. So why doesn't gamma minus 1 on its own do the trick? Well, it's because alpha is actually only a circle in natural units where c is 1. Otherwise, its domain goes way past 1, all the way to c, turning it elliptical. The same happens to gamma on our graph, and yet, no matter what units you're in, gamma itself remains a dimensionless variable. It doesn't get automatically scaled, so we have to do so manually. In this sense, the c squared can be thought of as nothing more than a conversion factor, merely a byproduct of using unnatural units. Anyway, with that, we've successfully derived the equation for kinetic energy, completing step 3. Combining it with the one for momentum, we can now accurately model relativistic block collision problems. This time, both quantities remained conserved, even in a different reference frame. But this collision is elastic. To begin step 4 of the derivation, we need access to the internal energy, so we're actually going to go back to the inelastic collision from earlier, where the blocks merge. From this point on, E0 is internal energy, K is kinetic, and E is total. As you'll recall, blocks A and B are each 10 kilograms and move at 0.5 c towards each other before merging into block C. With the newly introduced gamma in the formula, blocks A and B have slightly more momentum than 5c last time, but they still cancel out totaling 0, which matches that of block C after the collision. How about energy? Using the formula, total kinetic energy before the collision is 3.094 c squared, while after it's simply 0. This difference is no problem because the collision is inelastic, which means the internal states of the blocks are allowed to change. Since total energy is conserved, this loss in kinetic energy must be matched by a gain in internal energy. Whatever the total internal energy of A and B is, block C has that plus 3.094 c squared to conserve energy and momentum. So everything's normal so far, but what about in the other reference frame? Last time, block A only had 8c momentum, which was not enough to match at least 10c from block C. With the gamma in the formula, fast things get extra bonus momentum, so block A now has 13.333 c momentum. But if block C is 20 kilograms, even with the gamma, its momentum is only 11.547 c, appearing to violate momentum conservation. However, this is definitely the correct formula, and we've even verified it through the derivation and elastic example. That can only mean one thing: we made an assumption somewhere that we shouldn't have. The relevant assumption here is that the mass of block C is 20 kilograms. Since this collision is inelastic, the internal states of the blocks can change. This traditionally means their energy, but in relativity, the mass can change too. We can actually use conservation of momentum to calculate the mass of block C, and we find it's 23.094 kilograms, a bit more than the sum of A and B. This is not some kind of illusion. Block C really is 23.094 kilograms. In fact, it's its same mass no matter what reference frame you're in. It seems impossible for it to be more than 20, but it makes more sense when you realize block C is not simply A and B together. It's a brand new object created by an extremely energetic collision. It could also help to think in terms of particles, where C is a brand new particle created by the collision of A and B. Reverse time, and you have particle decay. The difference in mass before and after is known as the mass defect, and in this collision, it was 3.094. This number might be familiar because we've seen it before when calculating energy. Apparently, upon gaining 3.094 c squared joules of internal energy, the block system gained 3.094 kilograms of mass. This is not a coincidence, And it's also not unique to this example. In fact, we can actually use similar techniques to prove that for any particle collision, the product will have a mass defect equal to the change in energy, just without the c². Rearranging a bit, we officially arrive at mass energy equivalence equation form number 1. Delta E0 equals delta m times c². This is the same relationship we approximated earlier in the light wave approach, but this one is actually more universal. You see, particles interacting with each other by colliding and decaying like this is exactly how the universe interacts on a fundamental level. So this fact about particle interactions must also be true for everything composed of particles, aka everything. This means if you add internal energy to any object, it increases the object's mass by a proportional amount, and vice versa. This has massive implications. For example, even an otherwise unchanging metal cube is literally heavier when it's hot compared to when it's cold. Likewise, a spring weighs more in tension than relaxed due to elastic energy, and a flashlight actually gets lighter as you use up the battery's energy. In all three cases, the difference is too small to have a significant effect on anything, but it is still real. The same thing applies to protons and neutrons. Due to the intricacies of the residual strong nuclear interaction, they actually have less energy when bound together in a nucleus than apart, and as a result, each nucleus is a bit lighter than you might expect. That's why even though a carbon-12 nucleus is defined as exactly 12 Daltons, protons and neutrons themselves are slightly more than 1 Dalton. It's just that when you bind 6 of each together, energy decreases, and therefore so does mass. Bigger nuclei have more mass defect, but to determine what's energetically favorable, you have to look at mass defect per nucleon, in which case you actually get diminishing returns, and it peaks at nickel 62. That's why up until that point, fusion releases energy instead of costing it, but after, fission is more favorable. Now maybe you can accept that adding or removing thermal, elastic, chemical, or nuclear binding energy increases or decreases mass. But what about more exotic forms like electrical potential energy? Well, imagine a system of two opposite charged particles 1 unit apart. If you double the distance between them, it increases the electrical potential energy of the system. This energy doesn't exactly make either particle heavier, but it does make the system heavier. That's because it's stored in the electromagnetic field itself. If you were to treat them as one composite particle and try to accelerate that, you would find its mass is indeed greater than the sum of its components. That's because when you move the particles, you're also moving the electromagnetic field, or at least the disturbances in it. And so, even electrical potential energy contributes to mass. But what about kinetic energy? Well, it's only internal energy that contributes mass, so by definition, kinetic energy doesn't contribute. Or does it? You see, even if the object as a whole is stationary, parts of it can still be moving in what could be described as internal kinetic energy. One such example is temperature, which is just random movement of molecules. As we've seen, thermal energy does indeed contribute mass, even though it's technically kinetic. These examples really demonstrate an important point. All forms of energy contribute to mass. That raises an interesting question though. What even is mass to begin with, aside from contributions from internal energy? And if you remove those, what are you left with? Well, to answer that, it's time for the second equation form. The way we have it now describes changes in internal energy and mass. But what about total internal energy and mass? Normally you'd integrate, but in this case it's simple. If you graph E0 as a function of m, then delta E0 over delta m is just the slope of the function. Since that slope is just a constant c², the function must be linear with the equation E0 equals mc² plus b. And b must be 0 due to the simple fact that one full-size particle should have equal energy to two half-size ones when stationary, as that's the limiting case for slower collisions. This puts the y-intercept at 0, giving us E0 equals mc², which is mass energy equivalence equation form 2. According to this form, internal energy doesn't just contribute to mass, internal energy is mass. You could also say mass is internal energy. The only difference between them is the units, where c² is the conversion factor. There's only one potential issue with this process though. By graphing E0 in terms of m, we've essentially already assumed internal energy is purely a function of mass, nothing else, or perhaps vice versa. The main paper I'm using even called it an ansatz, meaning educated guess. Now, it's easy to accept this for fundamental particles. After all, they don't have any internal degrees of freedom aside from their mass, so really, there's nothing else internal energy can even depend on. For example, the mass of an electron is about 0.91 rontograms, and its internal energy is just that times c squared. In fact, fundamental particles usually use electron volts for energy and electron volts over c squared for mass, which saves us the step of converting. In this sense, mass and internal energy are essentially interchangeable, and for particles, we prefer energy. For larger objects, it is still true that E0 equals mc squared, and mass and internal energy are equivalent, but we usually split it up by accessibility. For example, instead of saying the battery has 2.1 quadrillion joules of internal energy, of which only 12,000 is accessible chemical energy, we treat this first part as mass, but the second as energy, even though it contributes a few picograms of mass too. But where does the starting mass even come from? To answer that, we're going to deconstruct the mass of an entire human person. After removing the negligible contributions from things like temperature and chemical energy, the vast majority of mass simply comes from the mass of the individual molecules. This in turn comes from the mass of the electrons and nuclei that compose it. The mass of each nucleus comes from that of individual protons, individual neutrons, and a negative contribution from the aforementioned nuclear binding energy. The reason the nucleons can lose mass like this is because most of their mass comes from varying sources aside from the mass of their component particles. The approximate breakdown is about 1% from the 3 valence quarks, 8% from virtual quarks, 32% from quarks' kinetic energy, 0% from massless gluons, 36% from gluons' kinetic energy, and 23% from the strong nuclear interaction field. So as you can see, even the mass of everyday objects, which we usually consider this static, unchanging concept, actually mostly comes from various dynamic types of energy, with only a small fraction coming from fundamental particles with intrinsic energy to them. It once again shows energy doesn't just contribute mass, it's what mass even is in the first place. So we've now seen mass contributions from pretty much every form of energy. Really, it's only direct kinetic energy that doesn't contribute mass. Or does it? You see, there's actually a sense in which kinetic energy does contribute mass, but to explain that, we need the next equation form. This one will actually be our simplest derivation so far. All we have to do is add together internal and kinetic energy to get total energy. As you can see, the -1 cancels with internal energy, and total energy is simply E equals mc squared times gamma. This is mass energy equivalence equation form number 3. According to this form, mass and energy are actually not exactly equivalent. Mass is equivalent to internal energy, but for total energy, there is a bonus multiplier equal to gamma. But we can actually bring back the equivalence using a concept known as relativistic mass. It's denoted mrel and equals rest mass times gamma. It essentially implies that mass undergoes a process analogous to time and space, mass dilation, where things get heavier as they approach c. If you use it, momentum is simply p equals mrel times v, matching the classical formula. Relativistic mass helps intuitively explain why you can't go faster than c. As you approach it, mass increases, and it becomes harder to push. It also explains F equals ma gamma cubed from earlier. It's one for time dilation, one for length contraction, and one for mass dilation. As for the total energy equation, the m absorbs the gamma, and you get E equals mrel times c squared. This means mass and energy are exactly equivalent, differing only in the units, no matter what form the energy takes. But relativistic mass is just a notational trick. Things don't actually get more massive when moving, right? Well, it's kind of meaningless to ask within special relativity. After all, you can't exactly weigh a moving object, you have to slow it down first. And besides, the only thing you're really measuring is force, which acts directly on momentum, not mass. Both of them already have a gamma, making relativistic mass just an unnecessary middle step. Modern-day physics doesn't really use relativistic mass at all, and they have good reasons for doing so. Energy without an adjective is usually taken to mean total energy. If you take mass with no adjective to mean relativistic mass, then yes, mass and energy are perfectly equivalent, but now you have two words for the same thing and none for the invariant one. If instead you take it to be invariant mass, the two words have more useful distinct meanings. But this decision has a significant and potentially confusing effect on mass-energy equivalence. Despite common claims that treating them as anything but exact equals is wrong, it's more accurate to say mass is a type of energy, the other being kinetic. But actually my favorite description is that mass is simply what you get when you take energy and make it stuck in one place. The literal equivalence is only applicable if you're only considering internal energy, in which case it should be E0 equals mc squared, or if you're using relativistic mass, in which case it should be E equals mrel times c squared. When using the conventional definitions, E equals mc squared with no subscript is not an identity. The accurate one has a gamma in it, and the form without gamma is only true for stationary objects where internal energy is total energy. Anyway, with that, we've fully explored the effects relativity has on the energy of objects with mass. But what about something without mass, like a photon? They famously carry energy. It's kind of their defining characteristic, and it's how we introduced energy loss in the first place. However, due to being massless, they have zero internal energy. This means the energy they carry must be kinetic. But if you try to use the formula for kinetic or total energy, you get the indeterminate form, 0 over 0. One interpretation is that this means photon energy can be whatever you want. And indeed, photons can have different energy depending on frequency. But to get the full picture, we need equation form 4. Our current form is pretty concise, but since it has gamma in it, there's technically a bulky square root in the denominator. How can we get rid of it? Subtracting and adding 1 splits it into kinetic and internal, but it doesn't get rid of the square root. To do that, we need to square it. Squaring both sides gives e squared equals m squared c to the fourth times gamma squared. If we now try the technique of subtracting and adding 1, gamma squared actually responds much more effectively to getting 1 subtracted from it. Giving them a common denominator, the 1's cancel, and we get v squared over c squared divided by 1 minus v squared over c squared, which is actually just v squared over c squared times gamma squared. Why is this useful? Well, take a look at what happens when we cancel and separate the c's and consolidate the squareds. We get mv times gamma, which is actually the formula for relativistic momentum, meaning we can replace it with p. And so, we've successfully gotten rid of gamma by absorbing it into another quantity that already includes it. In the process, we've derived an equation directly relating energy and momentum. E squared equals m squared c to the fourth plus p squared c squared. This is mass-energy equivalence equation form number 4. It's the relationship's final form and most universal. A stationary object has no momentum, but it does have mass, so that's where it gets its energy from, and the equation reduces. A moving massive object has energy contributions from both mass and momentum, with varying proportions depending on velocity. As for a photon, it has no mass, so its energy instead comes from its momentum. For massless objects, the equation reduces to E equals pc. But hold up a minute. How can photons have momentum without mass? Well, it's pretty much the same reason they have energy. The typical equation gives an indeterminate form, meaning it doesn't apply to massless particles, and the true source of momentum is more complicated. Since the energy of a photon is frequency times the Planck constant, and frequency is c over wavelength, momentum is the Planck constant over wavelength, which becomes the reduced Planck constant times the angular wave number, or in vector form, the wave vector. This is why massless photons still have momentum, and therefore can push things. Furthermore, the momentum vector must be in the same direction as the velocity vector, which is why we needed two opposite direction photons in the light wave approach. Or at least all of this is true for on-shell particles. Virtual particles from quantum mechanics are extremely weird and don't satisfy the equation, hence the name off-shell. But aside from force-mediating virtual particles, everything else satisfies the energy-momentum relationship. Due to this, momentum and energy are essentially forever intertwined in a single object called 4 momentum. In Minkowski space, the magnitude of 4 momentum is invariant and equals mass times 4 velocity, whose magnitude is also invariant. But we don't need Minkowski space to gain an intuition for it. All we need is a right triangle. If the sides have lengths e, pc, and mc squared, then the Pythagorean theorem gives us a beautiful relationship between them. Basically, energy comes from two sources. Massless photons are all momentum, while stationary things are all mass. In this sense, momentum and energy are actually very analogous to space and time. Stationary objects are all time and no space. As they move faster through space, they move slower through time, and photons are all space and no time. And in fact, according to Noether's theorem, conservation of energy and momentum arise from translational symmetries of time and space respectively. Now there's just one last important question you might have. Photons may not have mass, but they do have both energy and momentum. If that's the case, shouldn't they interact with matter just like things that do have mass, and therefore be affected by gravity and such? Well, indeed, photons are affected by the force of gravity, and a phenomenon known as gravitational lensing. If you remember back to the concept of relativistic mass, you can apply it to a photon by simply dividing energy by c squared to get the effective mass of the photon. The mass itself isn't important, since trajectory depends only on velocity, but having it simply exist provides a mechanism for massive objects to affect photons just as they would anything with mass. However, the amount of gravitational lensing predicted by this process is exactly half of what the results show in practice. But why though? Well, as it turns out, gravity is not a force at all. Instead, massive objects locally modify the four-dimensional curvature of spacetime, and what looks like acceleration from a force is actually just the tendency to follow a straight line through that no longer flat region. This is the core principle of general relativity, and it explains gravitational lensing, as well as other anomalies like orbits losing energy, gravitational time dilation, cosmological expansion, and the most mysterious places in the universe, black holes. I might cover general relativity someday, but the jump in difficulty from special to general is pretty big, so for now I'm content with providing the best explanations of special relativity ever seen. Speaking of which, this series has been 4 years in the making, and it's finally done. I'm still going to make a compilation video, but it will be a while due to wanting to go back and change a few things. Part 9 was probably the hardest script I've ever written, but I'm extremely proud of how this episode and the entire series turned out. Despite being, in my opinion, my finest work, relativity has never been the most popular, so if you think this was a good analysis of E equals mc squared, I would extremely appreciate if you like and comment, or share the video with any physics enjoyers you know. Thank you for watching, and I'll see you next time.